Hello everyone, my name is Paul Fowler. I'm with, we're going to do a lot of acronyms today, and we're going to cover some abbreviations and definitions and so on. So I'm with WIST at UWSP. What does that mean? The Wisconsin Institute for Sustainable Technology at the University of Wisconsin-Stevens Point. So that's a little bit of a mouthful. So we call it WIST and we call it UW-Stevens Point or UWSP. Thanks to SPC and the opportunity to present and talk with you guys today. I want to try and keep this quite interactive, so if there are questions that arise as I go through this set of slides, then do please raise your hand or use the cards, and we'll try and address them right then and there. My presentation today is, is entitled Bioplastics, a family of different materials. And we're going to get to why we call it a family in a little while. But first up, I'm just going to ask you all a question. Can you shout out some plastics for me? Just shout out the names of some plastics. Great. Others? So I got PVC, nylon, polypropylene, polyethylene, ABS, polyamide. Shout out some polylactic acid. Shout out some bioplastics. So I hear PHA, I hear PET, I hear cellophane, I hear PEF. So here's why we say a family, because bioplastic isn't just one thing, like conventional plastics are not just one thing. It's a really broad and diverse range of polymers that comprise this class of materials that fall into a broad category known as bioplastics. So lots and lots of different molecular structures, different names, different functionality that come within this very broad category known as bioplastics. So what is it that brings them together as a family? Well, two defining traits, and these are the only sort of characteristics that are common to them all. They may be bio-based and they may be biodegradable. They're going to be one or the other or both, right? Maybe bio-based, maybe biodegradable, maybe both. That's important, and we're going to sort of keep re-emphasizing that as we go through this presentation. So, bioplastics, right, is a contraction, and it's something of an ambiguous contraction of bio-based plastics and biodegradable plastics. And there's no ASTM or ISO standard definition of bioplastics, and it can be taken to mean both. Now, European Bioplastics and the Society of the Plastics Industry have come together, or they are essentially consistent in their definition of bioplastics being comprised of bio-based materials and biodegradable plastics. So bio-based. What is bio-based? That refers to materials which in some form they have been sourced. Their beginning of life, their source is from maybe in whole or in part from biomass, and that can be from agricultural crops, it can be from waste materials from forest products, it could be forest products grown particularly for the production of bio-based materials, and it can be from animals too. And then that if it's bio-based, that implies that the fact that it's based on bio implies that it may have undergone some sort of physical, chemical, or biological treatment. Biodegradable. Okay, this refers to the ability at the end of life for a material to break down safely and relatively quickly by biological means into the raw materials of nature. And there are petroleum-derived polymers that can biodegrade. There are bio-based materials that won't biodegrade. So that's a very, very, very important distinction to be aware of. Bio-based does not equal biodegradable. That's still remains a pretty common misconception amongst a number of different parties throughout various supply chains. So if you remember one thing from this event, please do remember that bio-based does not equal biodegradable. This you may see this sort of representation, this sort of quadrant in a number of different formats. But what it points out is you have essentially beginning of life. Where does the polymer originate from? Is it bio-based or is it petroleum-based? And then at end of life, when it comes to disposal or end of life management, is that material non-biodegradable or is it biodegradable? So this quadrant just kind of, it's by no means a comprehensive list, but it calls out examples of materials in the top left quadrant that are bio-based. For example, bio-based polyethylene, bio-based polypropylene, bio-based polyamide, PTT, polytrimethylene terephthalate, PET. There are examples of all those materials that can be made in whole or in part from bio-based starting materials. The bottom left quadrant is intended to represent conventional polymers that largely based on petroleum materials. And conventional polymers, we mean things that happened the turn of the 20th century when the petroleum industry started to evolve opportunities around nylon and polyethylene and polypropylene. So by conventional polymers, those are what we mean. And by conventional, we don't mean mundane or the fact that they're somehow pedestrian. These are the conventional polymers that have served their purpose really well since the explosion in the petroleum industry. In the top right-hand corner, we have examples of materials which are both bio-based and biodegradable. And again, this is not a comprehensive list, but it's just to give you a sense of some of the types of polymers and structures that are out there. So we have PLA, polylactic acid, PHA, polyhydroxyalkanoates, starch blends, cellulose, and polyhydroxybutyrate, which is a subset of polyhydroxyalkanoates. PHAs are a kind of a family in their own right of polyhydroxybutyrate, polyhydroxyvalerate. Both biodegradable and bio-based. And then down in the bottom right-hand quadrant, polybutylene adipate terephthalate, PBAT, petroleum-based, but demonstrably biodegradable according to certain test methods. And I'll come on to that a little bit later on. The same for polybutylene succinate, the same for polycaprolactone. Now there's crossover across these quadrants as well. These quadrants are not necessarily mutually exclusive. So there are examples of bio-based polybutylene succinate. There are examples of wholly or in part bio-based polybutylene adipate terephthalate as well. So these quadrants, the examples that appear in there are not necessarily exclusive to those quadrants. There's an opportunity for crossover too. So that often we hear about, we talk about biodegradable bioplastics from the point of view of them actually being compostable. And those terms are often used interchangeably, biodegradable and compostable. And biodegradable is something of a vague term, difficult to measure and define and apply metrics to. So compostable is a more favored terminology around compostable bioplastics, because composting is essentially a subset of biodegradability. So composting is one environment under which the act of biodegradation may occur. And compostability essentially applies some boundaries to biodegradation. So it qualifies the environment under which biodegradation takes place, and it quantifies the time frame under which biodegradation takes place. And another feature of it is that biodegradation occurs safely. So if you think back to my slides about biodegradation, we talked about relatively quickly, we talked about returning to the molecules of nature, and we talked about doing it safely. So compostability really is just one subsection of biodegradability. But it's an important one, because it's the one that you'll hear about later today, is the one on which you base compostable marketing claims. It's the one where there are pretty well recognized standards, both in Europe, in the US, in Asia, around the conditions under which materials can be deemed to compost. I want to talk about thermoplastics and thermosets a little too. Thermoplastics are typically the sort of packaging plastics that we're familiar with. So thermoplastics this is an important definition. They soften when they're heated, and then they become hard again when they cool. And that process can happen many, many times, generally speaking. They soften when they're heated, harden when they're cool. That makes them amenable to a whole range of different processing conditions in order to form various packaging materials. So they can be remolded, they can be recycled. So thermoplastics are a really very, very important part of the packaging scene, but also in terms of plastic processing generally, as opposed to thermosets. Thermosets are materials that cross-link when they're heated, and that forms an irreversible chemical bond. So think about things like urea formaldehyde, phenol formaldehyde, urea melamine formaldehydes, materials which are used quite a lot in the construction industry, in particle board production, in oriented strand board production, where you want to form a very durable bond that is not going to break. A feature of that is that those materials cannot be remolded or recycled. Thermopolymers and thermosets are all categories of plastics, right? So there's another sort of element, another sort of nuances there around bioplastics. So there are bio-based thermoset materials as well as petroleum-based thermosets. A little bit about drop-ins and additives. So a drop-in bio-based replacement. What this group of materials is essentially those conventional polymers made wholly or in part from bio-based monomers, intended to replace interchangeably the conventional polymers that are currently incumbents in various applications. So things like biopolyethylene, bio-PET, those materials which have that bio sort of prefix to them are functionally and molecularly the same materials. Okay? So by replacing a petroleum-derived polymer with a bio-based one, when the chemical structure is exactly the same, when the functionality is exactly the same, you're essentially doing a drop-in. You're switching one material out for another without any substantive changes to processing conditions, to any handling conditions, to any health and safety considerations. The bio-based material behaves essentially the same as a conventional polymer that it models, because structurally and chemically it's the same material. The only difference is the source of the carbon, which goes to make up that bio-based component. And that source is the feedstocks that we'll hear a little bit more about later today. So it's a new material, replaces the existing material with no change to the process, no change to production parameters, and no impact on the finished product. I wanted to touch on additives as well. Certain additives in plastics have gotten a bad rap, I guess. Bisphenol A being one of them. I'm going to talk about some which are peculiar to bioplastics in a little while as well. But additives are a really, really important part of polymer processing. And they can be present in bioplastics and conventional plastics in small quantities. They could be from a bio source, they could be from a petroleum source, but they do really important things. They help in the processing of polymers. So some additives are added to polythene or biopolythene, polypropylene, to help maintain thermal stability during processing. So when a polymer is extruded or compounded, if those additives were not present, you oftentimes can result in depolymerization of the polymer and subsequently weaken that polymer. So those heat stabilizers are important just for that sort of very transient process of thermoforming or injection molding or blow molding a material. Similarly, if you are thinking about some sort of deck application outdoors or plastic patio furniture, where those materials are going to be exposed to light for days or weeks or months or years, those polymers themselves are also formulated with UV stabilizers. So again, light, or UV light particularly, can very, very quickly start to break down the carbon-carbon bonds present in polymers. And so those light stabilizers are absolutely important from the point of view of durability, shelf life, long-livedness of a product. Plasticizers as well. Materials that are unplasticized, and you might think of PVC as being a really great example. Unplasticized PVC used in siding, in guttering and so on. Very, very stiff material. Plasticizers are added to PVC in order to make it flexible. So think of formerly Saran wrap, which was PVC based. Very, very flexible and stretchable. Thanks to the addition of plasticizers. So again, plasticizers is very, very important from the point of view of extending the range of properties or tailoring the properties of a particular polymer. And this slide applies to conventional plastics as it does to bioplastics. And then pigments and dyes, coloring those materials, making them opaque, all important additives. So additives are a good thing, generally speaking. There's a class that I did want to talk about, though, of biodegradable additives, and these are materials that have come into the marketplace in a number of different guises. They're known as degradable additives, they're being called biodegradable additives, oxo-degradable additives, oxo-biodegradable, photodegradable, photo-oxo-degradable, for example. And then there's probably some other nuances on that as well. I coloured this slide red, or Charlotte coloured this slide red as a sort of a caution to everyone in the audience. Because these so-called biodegradable additives are claimed to make a conventional non-biodegradable plastic biodegradable, right? So it's a magic fairy dust that you add into a polymer and it creates a biodegradable material. So you could add this to polythene, you can add it to PET, and those materials magically biodegrade. That's not what happens, in fact. These materials just cause fragmentation of those polymers. They don't cause biodegradation, according to those definitions that we had earlier on, converting the materials back to the molecules of nature in a safe sort of way. They simply cause the fragmentation of those polymers into smaller pieces. And those smaller pieces themselves do not biodegrade. Furthermore, the claims that are being made for these materials are not rigorously supported by sort of accepted test methods. And plastics which are have these additives incorporated into them are no longer suited to end-of-life management like reuse and recycling because of the impact that they have on the structure. Remember when I was talking before about UV stabilizers and heat stabilizers where the polymer chains break down, and those materials are there to prevent that breaking down. These are the opposite of that. These bring about, or they precipitate the cleavage of those polymer chains to break polymers down into fragments. So if you're a polyethylene or a PET recycler and you're looking to recycle those materials, reuse them again, then the presence of a biodegradable additive is essentially a no-no because it's going to weaken your polymer chain as you go through subsequent rounds of processing. Any questions on biodegradable additives or anything that I've said so far?
Can I ask a question?
Kim.
If it's a drop-in, can you assume it's recyclable? Is that a fair assumption?
If you're dropping it into a system that previously was in part of a recycling infrastructure, yes, you may, yeah. So let's have a look at some of the feedstocks that are used to manufacture bioplastics. Large class of bio-based polymers called carbohydrates, and within those there are some great examples around cellulose, industrial starches, glucose, sugar, and I know that Erin is going to talk about some sort of feedstock sustainability things later on. But these materials, cellulose can be derived from lignocellulosic biomass, from the forest products industry, from ag waste and so on. Industrial starch is typically grown for the specific purpose of feeding in industrial starch markets like pulp and paper industry. But then opportunities to take those industrial starches and further process them into thermoplastic starches, hydrolyze them into things like glucose, which also appears on this slide as well. And sugar. Sugar from sugar beet, sugar from sugarcane also serve as starting materials for the building blocks to make bio-based plastics. Biogenic methane has come to attention recently. So I talked about biodegradability earlier on and focused particularly on composting. When you take biodegradable materials in the absence of air and allow them to be acted upon by microbes, then a different process occurs whereby methane is produced rather than CO2 and water. It's methane, a little bit of CO2, maybe some carbon monoxide and some water too. But anaerobic digestion is a route into biogenic methane. So think about landfill waste, where that landfill waste is typically categorized, the methane arising there is typically categorized as biogenic methane. Ag and forest waste that could be anaerobically digested on purpose. Syngas is another route whereby under high temperature in the presence of a small amount of oxygen, gases like carbon monoxide and hydrogen are generated, and there are some pre-commercial or even commercial operations that are generating syngas. Sometimes you hear of that as processed gas. True syngas is made with a small amount of pure oxygen. That is expensive, and so air is typically used, and that processed gas contains necessarily some nitrogen. But it's a way to get into building blocks of molecules, carbon monoxide, hydrogen, which you can then go on and convert using conventional chemical techniques into feedstocks for bioplastics. I'm going to talk about some of those starting materials a little bit later on too. Others. Plant oils are a really important feedstock for biopolymers, whether it's certain vegetable oils in the production of thermoplastic starches, for example, some of the technology developed by Novamont. We talked about nylons before. We talked about bio-based nylons. And castor oil is used in large quantities for the production of certain bio-based nylons. So those plant oils are very important. And I think that Arkema, which makes a number of bio-based nylons, is probably one of the largest producers of bio-based feedstocks worldwide from the point of view of bio-based nylons, which have been in the market for quite some time now. Wastewater and sewage. Essentially any source of fermentable material, no matter how yucky it might be, can serve as a feedstock for bio-based plastics. And we saw some technology out of Micromidas, which is in the early days, converting wastewater and sewage into the building blocks for polyhydroxyalkanoates. Micromidas has kind of switched focus a little bit and changed names, and we'll talk about that a little bit later on. I put question marks besides carbon dioxide and petroleum. Who thinks that petroleum is a source of bio-based plastic? I do, because if I go back to my definition, right, of biodegradable polymers, where they can be based on petroleum feedstocks, then petroleum, under that definition, is a source of bioplastics, right? Did I just say that right? Who thinks petroleum is a source of bioplastic? That's what I meant to say. That's a different question. Who thinks petroleum is a source of bioplastic? Great. For all the reasons that I just said. That was a deliberate mistake to see who was listening. And what about carbon dioxide? Yeah. So there can be both biogenic sources of carbon dioxide, but also the opportunity to make biodegradable feedstocks, biodegradable materials from the stack gases of cement making plants, for example. So all of these that we've categorized as others give an example just of that variety, that diversity of materials that are used as feedstocks for bioplastics. So let's get into some of the classes of materials. Within this sort of chart here, under bioplastics, we've categorized 4 different groups. And I'm going to run through these groups in a little bit more detail shortly. But we have conventional polymers made from bio-based monomers. And remember, way back we talked about conventional polymers being things like polyethylene, polypropylene, nylon, PET, and so on. Then we have biopolymers made from biomass, which has been subsequently modified. Let me say that again. Biopolymers from biomass that have been subsequently modified. Then totally new, novel polymers made from bio-based monomers. And then finally, those polymers from petroleum sources that are biodegradable. So here's a list, and this is probably as comprehensive as it's going to get of conventional polymers made wholly or in part from bio-based monomers. So if you see something that's not on this list, please tell me, and I'll add it for subsequent events. But up there we have polythene, made from bio-based ethene. PET, polyethylene terephthalate. Polytrimethylene terephthalate. The difference between PET and PTT is just one methylene group, one CH2 group in the diol that goes into making these materials. PTT is commercialized as a resin called Sonoma, which is used in carpet fibers and so on. Polybutylene succinate. Here, the feedstock for that material can be wholly or in part from bio-based monomers. Polybutylene succinate adipate. And we'll talk a little bit about the various different monomers that go up go into making these polymers in the next slides. Polybutylene succinate terephthalate, PBAT, Ecoflex, a registered trademark from BASF, and then various polyamides, PA6, PA11, PA410, 510, 610, 10, and 10. Polyurethanes, those thermoset materials, which are made from bio-based polyols, but also have included within them isocyanates. And isocyanates, to date, have not been made from bio-based sources, but the bio-based polyols are pretty prevalent, and so bio-based polyurethanes for foaming applications are out there as well. And then unsaturated polyesters, opportunities around unsaturation of fatty acids and triglyceride oils from vegetables going to make unsaturated polyesters. So the monomers on which these materials are built and which are bio-based are things like ethylene glycol, 1,3-propanediol, butadiol, succinic acid, adipic acid, furan dicarboxylic acid, terephthalic acid, and sebacic acid. I'm just going to run through those materials one by one right now. So ethylene glycol. This is a really important, sometimes you see it written as MEG or MEG, or hear it referred to as MEG, but ethylene glycol is one of the building blocks of PET. So PET is a polyester, and it comprises two component monomers, which are then chemically linked together and polymerized. One of them is ethylene glycol. The other one is the one on the bottom, second to the bottom of the list there, terephthalic acid. So ethylene glycol can be wholly bio-based, comes through a process starting from ethanol, where ethanol is first dehydrated to ethene. It's then epoxidized to ethylene oxide. It's then ring open. It's turned into a carbonate, and eventually you get to monoethylene glycol, bio-based. So it's a multi-step chemical process to get to ethylene glycol from ethanol. And bioethanol itself, remember, coming from the fermentation of sugar. So it's quite an involved process to get from ethanol, which itself has come from a fermentation route, to ethylene glycol. The first thing I said there, if you remember, was ethylene glycol is dehydrated to ethene. Now, I don't have ethene on that list, but ethene or ethylene is the building block for bio-PE. So bioethanol serves as a really important precursor molecule for the production of things like bio-PET and for bio-PE. Propanediol, I think probably DuPont and Tate & Lyle commercialized some fermentation technology around converting glucose to 1,3-propanediol. I talked about polytrimethylene terephthalate earlier, and the only difference there being one additional CH2 group in the structure. So ethylene glycol is a hydroxyl group, CH2, CH2OH, 1,3-propanediol just has another methylene group present there. Butanediol is yet another methylene group present. And production of ethylene glycol, 1,3-propanediol, commercialized. Butanediol can come from a reduction of succinic acid. Succinic acid is a 4-carbon diacid. If you reduce that, you get back to butanediol. But there are some routes now starting to emerge of going directly from sugar to butanediol, and I believe Novamont is investing heavily in a plant to go direct from glucose to butanediol. So without first making succinic acid and then going right the way back to butanediol. Succinic acid, a number of players in that space. DSM Roquette, Miriant, others are active in the space of succinic acid. And succinic acid being a key sort of building block for polybutylene succinate, but also involved in production of nylon too. Adipic acid is C6 diacid, and routes to adipic acid have been developed, commercialized by, amongst others, Renovia and Verdesign. Furan dicarboxylic acid is the building block of something which you may be familiar with, PEF, polyethylene furanoate. And this is a material as well which is coming from bio-based source. Terephthalic acid is the big one, is one of the big ones right now. It's the other component part of polyethylene terephthalate, the other component part of PTT. And there are a number of efforts underway to get to a wholly bio-based terephthalic acid structure. Companies involved in that sort of space are Virant in Madison, which was acquired just last year by Tesoro, a Fortune 100 refinery company out on the West Coast, and acquired with a view to looking at biofuel production, but also looking at ways to accelerate their production of a fully bio-based terephthalic acid. What does all this mean in real life? So if you pick up a plant bottle or Dasani water bottle that's been made of PET, you'll see on there that it has some bio-based content up to 30%. And why does it say up to 30%? It's because of those two components. You have a bio-based component in the ethylene glycol, and you have a petroleum-based component in the terephthalic acid. And if you take the molecular weights of those materials and add them together, and then you take the molecular weight of the ethylene glycol and divide that by the total weight, you get to around 30%. They say up to 30% because you cannot always ever be sure that you have included entirely bio-based ethylene glycol in the production process. So to get to 100%, you have to get to 100% bio-based terephthalic acid. So Virant is operating in that space. Gevo is operating in that space as well with a product they have, isobutanol, which they're taking through various chemical steps via isobutene and octene, and then doing some work to get into a terephthalic acid derivative. I mentioned Micromidis before as well, and the fact that Micromidis started out life converting sewage to polyhydroxyalkanoates. A few years ago, they switched some of their focus into trying to get to a bio-derived terephthalic acid, and they're coming at that through a sugar to a dimethylfuran route, and then doing a so-called cycloaddition with ethene to get into terephthalic acid. Their new name is Origin Materials. And then sebacic acid typically occurs predominantly in the nylon space. So that's a C10 dicarboxylic acid. And if you remember back a few slides, I was talking about various different nylons, 410 and 510 and 610. The numbers there refer to the number of carbons, first of all in the amine chain, and secondly in the dicarboxylic acid chain. So wherever there's a 10, it's talking about sebacic acid, a C10 dicarboxylic acid derived from castor oil. So it's operations on castor oil. Castor oil is not a food oil, so no concern about diversion of food sources for the production of castor oil, and something that's been a very well-established process. And those, the 4, the 5, and the 6 essentially refer to the diamine components, which can then also be bio-derived. So what about biopolymers from biomass subsequently modified? Within this, I've categorized cellulose, whether that's regenerated cellulose film, such as that produced by Futamura, or cellulose acetate or cellulose diacetate from the likes of companies like Celanese. And then thermoplastic starch blends. So here you take the whole polymer and you've not done anything you've not hydrolyzed it or broken it down in any sort of way. You've used the polymer essentially as is and made some modification to that. So in the case of the cellulose, you've done some chemistry on the on the cellulose polymer to solubilize it and then cast a film and regenerate that cellulose film. With an acetate, you've reacted it with an acetic acid derivative to make essentially the same polymer, but it's been substituted with acetyl groups, and the diacetate is just more substitution of that cellulose polymer. But the polymer itself has not been substantially degraded or altered. So it's subsequently modified. And the same for thermoplastic starch blends too. Here you have a starch and you've somehow plasticized it by adding plasticizers, which I talked about earlier before, glycerol being one of those, one of the pool of materials that can be used to plasticize starch, along with vegetable oils and a range of other materials. Then there are those materials that I classified as novel polymers from bio-based monomers. And within that group, we categorize polylactic acid from I guess, big players in that space would be NatureWorks and Total Corbion. Polyhydroxyalkanoates, and I talked about those earlier, being a subset, being a classification with a subset under there of polyhydroxybutyrate, polyhydroxyvalerate, and I believe Danimer Scientific is here today, and they're in that PHA space, amongst others too. And then polyethylene furanoate is a material which is kind of gaining some attention, traction right now. Joint venture between Avantium and BASF to commercialize what they call the ICSI technology. But the polyethylene furanoate is again a polyester derived from carbohydrate sources, and the monomer there is something called furan dicarboxylic acid, which we looked at earlier, and derived by a bio-based route. And then there are those bioplastics from petroleum sources that are biodegradable. Polycaprolactone, polybutylene succinate, polybutylene adipate, terephthalate. Now there are activities underway to essentially swap out the petroleum-derived materials. For example, in the adipate, in the PBAT example, bio-based adipic acid to substitute for the conventionally derived adipic acid. So this is just really a, sorry, go ahead.
Are there any companies commercially producing bio-based adipic acid?
It's in development. To the best of my own knowledge, the answer to that is no, but Renovia is working in that space, and Verdesign are working in that space. And there may be others too, but I don't know of any commercial bio-based adipic acid right now. So, as we went through that survey, you can see that conceptually any conventional polymer, whether it's polyethylene, whether it's nylon, has the potential, at least from a chemical standpoint, to be made from bio-based materials. The hurdles and the challenges are not necessarily around how you do that technically or chemically, but it's really around the economic feasibility of getting to that point. But this is important, that when we were shouting out the names of those various bioplastics and plastics at the start, there was a lot of crossover, and there's fundamentally, from a chemistry standpoint, no reason why any conventional polymer could not be made from bio-based sources. And that's a sort of a really forward-looking statement, but it's important from the point of view of understanding that from a functionality and a structural molecular point of view, conventional polymers, bioplastics can be oftentimes interchangeable. So I'm going to summarize right now. Bioplastics are a family of polymers almost as diverse as conventional plastics. And we saw that right at the start of the presentation, right? As you all were saying, well, here's some examples of bioplastics. The bio in bioplastics may refer to the beginning of life, i.e. the origin of the starting material, is it bio-based, or it may refer to the end of life management, biodegradable. Bio-based does not equal biodegradable. And the bioplastic family provides opportunities for drop-in replacement of conventional plastics, but at the same time it gives us novel, new-to-market polymers with various points of differentiation, whether that be compostable, whether it be anaerobic digestible at end of life, whether it be functionality, performance in use. I'm sure if you speak to the guys from Sinvina about PEF, they will tell you about the functional performance advantages over PET. So it's not just about end of life, it's about performance in use, it's about aspects that I'll come on to in a presentation after the break in terms of some of the characteristics of these materials, which are the most important really, performance in use. So there are these new to market polymers with various points of differentiation. And I'm going to stop right there. Questions?
This bio-based PET bottle you talked about, is that compatible with regular petroleum-based polymers?
Absolutely. Yeah. It can enter the recycling stream just the same as a
You can mix both the petroleum-based and the bio-based.
correct. Yep. I know.
When you just have partial bio-based components, is there a convention associated with naming that or calling that something? If it's called a biopolymer, is there an amount?
You know, I think Adam may talk about that toward the end, but there are certainly methods for establishing how much bio-based carbon content there is in there. And then, so once you establish how much bio-based carbon there is in a partially bio-based material, whether it's 1%, whether it's 10%, whether it's 100%, there are different ways that you may then interpret that. I mean, in certain jurisdictions, there are efforts to say, well, you have to be above a certain level. But at least there's a means, first of all, of establishing what's the content, and then there's this sort of subjective part around at what point does this become something which we can call bio-based.
So would you add plant oils like castor oil to the list of bio-based monomers? Because it's directly used as a polyol and vinyl
Yeah.
esters and polyurethane.
Yeah, it's usually, I would. I mean, I put sebacic acid, which was coming from castor oil, but I would add castor oil itself, yeah. Thank you. I shall add it to the list. Other questions? Okay, well, thank you for your time. I shall be around at the break and tomorrow if anyone has questions that they would like to ask offline, but for now, thank you.